Hello, my name is Nikolai Zolotych. I'm a professor at Lobachevsky University of Nizhny Novgorod, Russia. Today I want to present you some results concerning the concept of stochastic separation. This is a joint work with my colleague Sergei Sidorov, and we would like to thank Professor Gorbайн for useful discussions. We start with the concept of linear separability. A set of points x1, x2, and so on, xn, is called linear separable, or one convex, or convex independent, if the set of vertices of their convex hull coincides with the points themselves. Or equivalently, the set of points is called linear separable if each point in the set is separated from all other points by a hyperplane. Let's consider 4 random points in the disk. These 4 points are linear separable. All these points are vertices of their convex hull, and each point can be separated from all other points by a hyperplane, by a line. If we consider, for example, the following 6 points, they are not linear separable because this point is inside the convex hull of all the points, and this point cannot be separated, cannot be linearly separated from all other points. Now consider so-called Sylvester's question. This is a question which this mathematician asked in 1864. What is the probability P of n and k that n random, independent, and uniform points from convex body K in the d-dimensional space are linear separable? Sylvester asked this question only for the case of 4 points and for a body in the plane. And a set of interesting results were obtained during 2 centuries. Blaschke proved that for every convex body K on the plane, the probability for 4 points in the convex body K is between that probability for 4 points for the triangle and for the probability for 4 points in the disk. In particular, the probability for 4 points in the triangle is 2/3. The probability for 4 points in the square is 25/36. And here you can see the probability for 4 points in pentagon, hexagon, and in the disk. The following 2 nice results were obtained by Walter and Perimhoff. These are the probabilities for n points in the triangle and in the square. For every convex body K in the plane, Barany found the limit for this quantity of this probability. The area of K is the area of the body K, and the A of K is the supremum, and A of K is the supremum of the affine perimeters of all convex sets S in the body K. I don't want to delve into the definition of what an affine perimeter is. I can only say that this is an affine invariant analog of the perimeter of a figure. We are interested in d dimensions. Barany and Furidy proved that this number of points in d-dimensional ball are linear separable with probability close to 1. The probability is greater than 1 minus alpha. On the other hand, if C is greater or equal to 20 and D is greater or equal to 100, then the probability that this number of points in d-dimensional ball are linear separable is less than this quantity. So if they have the following number of points in d-dimensional ball, they, with high probability, is not linear separable. Baran and Faraday formulated the following conjecture, that the threshold function for linear separability of random points in d-dimensional ball is about this number. So, if the dimension is high, then any point of the data set can be separated from all other points by a hyperplane with a probability close to 1, even the number of points is exponential in terms of dimension. This number is exponent of d. This number is the exponent of d. Such kind of results, valid for many other distributions too, are called stochastic separation theorems. These phenomena can be explained from intuitive point of view by the following observation. Let's consider a d-dimensional unit orange. The radius of the orange is 1 and the radius of the pulp is r. The volume of its pulp divided by the volume of the orange is r to the power d. This quantity tends to 0 as d tends to the infinity. So in d-dimension space, when d is large, the orange peel takes up too much space. Already for d equal to 3, this contradicts our intuition. For this three-dimensional orange, the radius r is equal to 2 to the power minus 1 divided by d, approximately 0.8. And only the half of the volume of this orange is in the pulp, other half is in the skin. So, if the dimension is high, then the data points are near to the border and far from the center. That is why when the dimension is high, then the points, even exponentially many points, are linear separable. Now let's consider the concept of Fisher-separability. The set x1, x2, and so on xn is called Fisher-separable if the dot product of x sub y times x sub j is less than of x sub y times x sub y for all different I and j. Or equivalently, the set of points is called Fisher-separable if each point x of I is separated from all other points by a hyperplane with a normal vector connected the origin with that point x of y. Fisher-separability implies linear separability, but not vice versa, even if the set is centered and normalized to unit variance. Consider these 4 points. They are linear separable, but what about their Fisher-separability? This line goes through the point xi, and it is perpendicular to the line connected the origin with the point xi. This vector is the normal vector for the line. The line has the equation xi times x is equal to xi times xi. The line divides the plane into 2 half planes. This half plane can be described by inequality xi times x is less than xi, and this half plane can be described by the inequality xi times x is greater than xi. All other red points satisfy this inequality, so the point xi is Fisher-separable from all other points. The same is for this point. This point is Fisher-separable from all other points. This point is Fisher-separable too. But what about this point? We can draw the line through that point perpendicular to the line connected the origin to this point. And you can see that this line divided all other points into two subsets. So this point is not Fisher-separable from all other points, and the whole set is not Fisher-separable. Estimates for the probability and for the number of points that can be Fisher or linear separable are obtained in several papers of these authors. In particular, for random points in the spherical layer, B sub d minus r times B sub d, so in the skin of the orange, the following results were obtained. The following lower bound for the probability that one point in the random set of points in the spherical layer is Fisher-separable from all other points. As a consequence, the following upper bound for the number of points was obtained. If the number of points is less than this quantity, then the probability that one specified point is Fisher-separable from all other random points in this spherical layer is close to 1, is greater than 1 minus theta. The following lower bound for the probability that n random points in the spherical layer are Fisher-separable was obtained, and as a consequence, the following upper bound for the number of points was obtained. What about other distributions? Similar results, stochastic separation theorems for Fisher and linear separability are valid for a wide class of other distributions. See the paper by Korpine, Grichuk, and Tukin. Roughly speaking, this class consists of distributions without sharp peaks in sets with exponentially small volume, including some classes of log-concave distributions. Estimates for product distributions are obtained in the paper by Grichuk. Now let's move to artificial intelligence. The concept of so-called curse of dimensionality is well known in optimization, numerical methods, machine learning, and in other fields of applied mathematics. If the dimension is high, then standard procedures that work in low dimensions don't work in high dimension. The following reasons can be indicated here. One needs exponentially more data to fill in a high dimensional space and to train machine learning models, because the volume grows exponentially with the dimension. This issue causes machine learning algorithms to fail if they have exponentially much data, or to overfit if they have not enough data. Other reason connected with previous one. Euclidean distance is intrinsically meaningless for high dimensions. The distances from the origin to the points is approximately equal. The distances between all pairs of points are almost equal. All two vectors from the center to the points are almost orthogonal. Due to errors in the data, we cannot determine, for example, distance between data points. So in high dimensions, many metric algorithms don't work properly. Here you can see the histogram for the distance for random points in the unit d-dimensional cube. You can see that the distance is concentrated around this quantity. So when the dimension is high, all points are on the approximately same distance from the origin. Here you can see histograms for the distance and the angle between all pairs of random points in the d-dimensional cube. This histogram is for distances between all pairs of points, And you can see that all distances are close to the quantity, approximately 25, 26. And this histogram is the cosine of the angle between all pairs of vectors. You can see that almost all vectors are orthogonal. The concept of the curse of the dimensionality is well known in contrast to the concept of blessing of dimensionality. The main principle here is the following. As we have seen, if the dimension is high, then with high probability the set of random points is linear or Fisher-separable, even if the number of points is exponentially large. In particular, for example, erroneous cases can be easily separated by Fisher discriminant when the dimension is high. The phenomenon of blessing of dimensionality has a lot of consequences and applications. And stochastic separation theorems have been widely used in machine learning for constructing characters and ensembles of characters, for determining the intrinsic dimensions of the data sets, and for explaining various natural intelligence phenomena such as the grandmother's neuron and others. Our new results concern with the random uniform distributed points in the spherical layer. Theorem 1 gives us the lower bound for the probability that one specified point in the set of random uniformly distributed points in the spherical layer is linearly separated from all other points. This probability is greater than 1 minus n divided by 2 to the power d, so it is very close to 1. As a consequences, we have the following corollary. If the number of points in the spherical layer less than this quantity, then this high probability more than 1 minus theta, the specified point in the set of random uniformly distributed points in the spherical layer is greater than 1 minus theta. Theorem 2 gives us the low bound for the probability that the set of random points uniformly distributed in the spherical layer is linear separable, and this probability is greater than 1 minus n times n minus 1 divided by 2 to the power d. So this probability is very close to 1. As a consequences, we have the following corollary. If we have less than this quantity of points, then this high probability more than 1 minus theta, this set of points will be linear separable. Here you can see the graphs for probability frequency that a random point is linearly or Fisher separable from a set of 10,000 random points in the spherical layer. The blue solid line corresponds to the theoretical bound for the linear separability, theorem 1. The red dashed dotted line, this one, represents the theoretical bound for the Fisher-separability obtained in Combine-Burton-Tukin paper. The crosses here, here and here correspond to the empirical frequencies for linear separability obtained in 60 trials for each D. And the circles here correspond to the Fisher separability. You can see that the probabilities that one specified point is linear and Fisher separable from all other points are quite close, and the theoretical bound for the linear separability approximates well the both probabilities, the both frequencies, linear separability and Fisher separability. Another important conclusion from the experiment is as follows. Despite the fact that both probabilities for Fisher-separability and for linear separability are close to 1 for sufficiently big D, the threshold values for such a sufficiently big D differ greatly. Here you can see the graphs for probability and for frequencies that the set of 1000 random points in the spherical layer is linear and Fisher separable. The blue solid line corresponds to the theoretical bound obtained here for the linear separability, and the dotted lines here represent the theoretical bound for the Fisher separability obtained by Gorbine, Burton, and Tukin. The crosses here correspond to the empirical frequencies for linear separability obtained in 60 trials for each dimension. And the circle here correspond to the empirical frequencies for Fisher separability. Here you can see similar graphs for probability and frequencies for 10,000 random points in the layer. As a conclusion, let's consider open mathematical questions here. We want to find more exact bounds for d-dimensional cube, for spherical layer, for other regions in d dimensions. The open question is, what is the probability that the points are linear separable but not Fisher separable? It is clear that this probability tends to 0 when d tends to infinity, but it's not clear what is the asymptotic. Another interesting and important question is the following. What is the threshold function for linear separability of random points in d-dimensional ball, d-dimensional cube, and spherical layer, and so on and so forth? Conclusion. We defined the bounds for the number of points and for the probability in stochastic separation theorems. We gave new bounds for linear separability when the points are drawn randomly, independently, and uniformly from a d-dimensional spherical layer or ball. These results refine some old results and allow us to better understand the applicability limits of the stochastic separation theorems for high-dimensional data mining and machine learning problems. One of the main results of the experiment comparing linear and Fisher separabilities is as follows. The blessing of dimensionality, when using linear discriminants, can come noticeably earlier for smaller values of d than if they only use Fisher discriminants. This is achieved at the cost of constructing the usual linear discriminant in comparison with the Fisher one. Thank you very much.